Hello everyone, I am Carlos Chick here. I will be presenting my exam 3, the last of the exam of the semester, for my process controls course, which will cover Cascade control system problems. Here we have question 1 with a given Cascade control loop with 2 PI controllers and 2 disturbances showed in figure 1. We will be answering 3 questions for this problem that will be shown in the following slides. Part A, the first question is design the inner loop controller as a PI controller. What are the values of the control parameters? And we will be targeting a bandwidth of 0.2 rads per second. Here we first want to find C2 first, which gives a control parameter for the inner loops are KB112 TI 0.841. The MATLAB code is located in the appendix at the end of this presentation. Here, part B. Second question is asked to design the outer loop controller SPI control. What are the values of the control parameter? And also we will be targeting a bandwidth of 0.2 rads per second. So here we find the outer loop C1 where the parameters of KB equals 2.1 by 10 to the negative 5 and TI equals 0.005. Now we have part C, where we plot the disturbance rejection response for the given cascade control design with all axes labeled and any relevant response characteristics. Is disturbance rejection achieved, and what is the value of the response offset? In figure label reference tracking, we have the set point tracking performance almost identical to each other. As you can see in the reference tracking, the cascade in blue is almost completely linearized when reaching an amplitude of 1, while single loop has more of a offset past the 1, but later once they reach about 40 seconds they start to linearize with each other. While in the disturbance rejection we have the cascade system outperforming the single loop. And yes, we do achieve distribution rejection, as we can see in the disturbance rejection graph. We see that the cascade, obviously as mentioned, outperforms the single loop. And the offset of the graphs is, as we're then looking at reference tracking, at 1. When looked at the graph linearized, but when the single loop versus cascade, the offset has a difference of about 0.1 at around 9 to 20 seconds before both linearize at the offset of 1. And just here to verify the questions that were answered. For is disturbance rejection achieved? Yes, disturbance was achieved. What is the value of the offset response? We have an offset of 1. But if we compare separately at 9 to 25 seconds, we have an offset difference of about 0.1. Now here we have another cascade problem for core question 2, where we have a combined feedback and feedback controller system, figure 4. We'll be also answering questions part A, part B, part C, which will be shown in the following slides. So here we have the first question for problem 2. What is the closed loop transfer function of y of s divided by y of s p of s if d equals 0, and y is p as a variable? So as we can see in figure 5, here we have a part of the system from figure 4 to show how to come up with the transfer function of y of s divided by y of p of s for equation 1, as shown on the right. As we can see in the first part of our numerator, the forward was known as the forward. You go off, if we go back to figure 5, we go for a start off point of YSP, the set points where we have Km, then next is times GC, times GV, times GP, as you can see in the numerator of equation 1. Then in the denominator, we use the 1 plus the loop, which is for our equation of the denominator. And in our case, we have 1 plus GC, GV, GP, and GM. Then we plug in our given variables given to the equation. As we see, g f of s equals 3 over 4s plus 16, which is considered a valve. Gd of s is 10 to the e of negative 5s over 4s plus 1, which is a disturbance transfer function. GPS equals 32e to the power of negative 5s divided by 54s plus 1, which is our process. Gm of s equals 2e of s divided by s plus 1, which is our transducer or our transmitter, or at times can be both. So we plug in all the given variables to our equation. The only one we do not add is gd of s, which is although it's given by the problem, the variable is not needed since d equals 0, and is now within the system to create the transfer function of y of s divided by ys of p of s. And we will need to simplify further in order to find gc. As you can see, gc is the only variable we are missing. And since our problem system has given us transfer functions for the value, in order to find value of gc, we have the valve variable given, which is gv, the transducer, which is gm, and gp, which is our process, or the transfer function we are given. So we can use the characteristic equation 1 plus loop, which is as shown under the Ziegler-Nichols method, which is 0 equals 1 plus gc, gv, gp, gm for our situation. Once we plug in the variables, we always have 1 plus all the variables given, only gc is missing. So here, once we have found where here we assume that gc will equal kc, and once kc is found, which is our ultimate gain, and then find our ultimate period, we can use the Ziegler method chart in order to create either a PI controller or PID, depending on the situation we need. Here we have part B for question 2. As you can see, we have a part of the system from the figure 4 to show how to come up with the transfer function of y of s over ds for equation 3 when y is p equals 0 and the variable d is an input variable. And the numerator is the forward, which is only gd. Then the denominator is 1 plus the loop, as similar to part A, which for our equation is 1 plus gc, gv, gp, gm. Now here we also have all the variables with given values. We have gv, a valve, gd, disturbance transfer function, gp, process, gm, transducer or transmitter, or both, where we plug in our variables, and we'll have to solve for gc in order to have a PI or PID controller. So here we have question 3. Why would an engineer choose a combined feedback and feedforward controller as opposed to feedback only or feedforward only controller? The first thing would be a feedforward would try to eliminate the effects of measurable disturbance, and when we have a feedback controller as well, it will correct for unmeasurable disturbance, modeling, and errors. If we were to, for example, just use a feedback itself, although some advantages would be like corrective action occurs regardless in requiring like knowledge about the process, there's disadvantages on its own that would be like control takes no corrective action until about a deviation, and another disadvantage would be control incapable of correcting a deviation from set point at the time of the detection, and theoretically is not capable of achieving perfect control. Now, if we were to go to a feedforward controller, although it has advantages, is theoretically capable of perfect control, takes corrective action before the process is upset control, but alone itself, its advantages are disturbance must be measured, requires more knowledge of process to be controlled. The ideal control that results in perfect control may be physically unrealized. This concludes our presentation. Thank you.